is V defined by the set of all vectors x, y, such that x times y is greater than or equal to 0, a vector space? So we want to begin by recalling that to determine if V is a vector space, we need to check, is V closed under addition? And is V closed under scalar multiplication? Remember that these two axioms alone guarantee that the remaining axioms hold true. So to get us started, we want to think to ourselves, what are we testing? So it can be helpful, if possible, to think about the geometric interpretation of what's given. So again, looking at this V, we see that the requirement of this set is that x times y must be greater than or equal to 0. So we of course know that this holds true in quadrant 1 here when x and y are both positive. So we're shading in quadrant 1. And we think to ourselves, does any other quadrant here make this hold true? So we know that if x is negative and y is negative, that this will also produce a positive value greater than or equal to 0. So the shaded region here is V as described above. Now let's go ahead and we'll incorporate some arbitrary vector u defined by the components x, y. And so the first thing that we need to ask ourselves here is this vector, or is V closed under addition? So what do we need to test here? We need to test that for all vector u and vector v in set V. Is the sum of these two vectors also in set V? And so to begin, let's simply let vector u and vector v be two vectors in V, the shaded region above. And we'll again start by thinking about this geometrically. So we have our vector u in quadrant 1. And again, just like that previous example, if we assume that vector v is also in quadrant 1, we can use our parallelogram rule to show that the sum of these two vectors is also in V. But we can't always assume that these two vectors will be in the same space. So what about if we keep vector u here in quadrant 1, and instead suppose that vector v lives down in quadrant 3, right, which is also part of V. So again, using our parallelogram rule, from the terminal point of view, we can draw a parallel vector V, and by the parallelogram rule, we can see that the sum of those two vectors, u plus v, is not in capital V, or not in that space. So we can say that, therefore, V is not closed under addition. Right, we've shown that vector u plus vector v is not in capital V. So that means that not all of the axioms will hold true. So if capital V is not closed under addition, this allows us to conclude that V is not a vector space. Right, so thus far all we've done is think about this geometrically. But we could also incorporate test points if we want to make sure that this holds true. So let's take a look at that. And so let's give ourselves enough room here. So let's suppose that we wanted to test this algebraically. So keeping in mind that original shaded region, so here we can incorporate another quick graph. So here is the x and y axis, the x-axis, and we know that V, as described above, includes quadrant 1 and quadrant 3. And then since we're testing this algebraically, let's incorporate a scale. So say 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Right, so we're doing a 1 by 1 scale. So you want to pick two vectors that exist in the shaded region, capital V. So let's suppose we'll do vector u is defined by the components 2, 2, and vector v, let's do is defined by the components -1, -3. And we can go ahead and sketch these. We know vector u, so 2, 2. Here is vector u. And vector v is -1, -3. Alrighty, so testing this algebraically, we need to take the sum. So I have vector u plus vector v is the vector 2, 2 plus the vector -1, -3. And adding up those like components, I have 2 minus 1 is 1. 2 minus 3 is -1. And so if we really wanted to confirm this, we could sketch this graph. We can say here is the new vector, vector u, plus vector v, which we can see lives in quadrant 4. Right? It is not in the shaded region. So this is not in that set V. So V is not closed under addition. And because the vector operation of addition does not hold true, it tells us V is not a vector space. And we are done. So depending on the set that you're given, you can test things algebraically like we did here, or you can test them geometrically.